Okay, so we start our second part, our lecture here. So, right now, if we are assume, because you can see here the equation here. Wait a minute. So you can see the equation 4.55. So what's this meaning? Because we have this one. Because we have a trigger signal. According to the model here, so you can see according to the model, we have a trigger signal, original trigger signal. So this one is your long-term prediction. Long-term prediction, J equal minus I, Bj. This one R is we call the residual signal. Invert, so they are remove LPC signal. So this one is you try to using LPC signal according your original signal. So this R, what's this R? This R is residual signal, original signal remove. So our original signal, original signal. So we are trying to remove LPC synthesis, synthesize signal. So we call this one is a residual, LPC residual signal. So residual signal, we try to trigger, try to find long-term prediction. This one is we call the short-term prediction. So and then this one is trigger signal. We assume this trigger signal close to zero. So we hope to approximate this one. So you can see we try to approximate this one. So this one we call this signal minus this signal minus all of this signal try to become minimized. So we define this one is our error signal. So you can see our error signal, this one close to zero. So this one should be approximate by this term and this term. So we come out like this equation. So this S of n minus this synthesized speech signal. So this one minus this one is R of n, So they try to make sure you can see your error vector become R of n, try to become minus I, J equal minus I, beta J, and residual signal n minus tau minus J, because we didn't know which delay, which pitch information. So we're using beta J and tau here. So because this signal minus this signal minus this signal become the residual signal, So residual signal, we are residual signal move long-term movement, and then neighboring sample do the linear combination and multiply by their gain, and then do the prediction. So we try to find the best match. So we try to find the best match, T and best match tau and best match beta. So according to this issue, we have two unknown, two different type parameter. Try to find the best value. So they have one method called the one-shot optimization. So we assume the pitch spectrum information of a residual signal is close to, could be close to your pitch spectrum information. So we can substitute for your alpha J as before, because this one is look like if we are consider tau is fixed. So this one is look like if we consider should be look at if we are consider this one a specific value. So So we can see this one is look like a linear prediction. Linear prediction, so they become the metric equations. We try to figure out the metric solution. So metric, this one will become the metric. So your beta, and then so you, because this one is look like a linear prediction. What we solve linear prediction become a metric problem. So we try to find the inverse metric if your tau is given. So we can solve for alpha as before and use the residual from LPC coefficient estimate to minimize the intermediate residual energy. So the pitch filter coefficient, are then found using this intermediate residual signal. This procedure can be near optimal provided by long-term lag. We call this lag is greater than analysis frame. So once your tau is bigger than your speech frame, this one is okay. So you're using one-shot optimization. So you look like what's the one-shot. So we assume the pitch spectrum information based on R of n. So they are close to close to your pitch spectrum information. So we are based on the residual signal. We are first issue, we try to get alpha. This one we call the beta. This one we call the alpha. So we try to get your linear prediction coefficient first. So we try to get your linear prediction coefficient first, and then use that one. We get the LPC inverse filter, and then we get the inverse filter. So these two are subtracted. So we get a residual signal. So we get the residual. So after go through LPC inverse filter, and later on we determine beta I and tau. So this one we call the just first iteration. So this one is one step by step. First step we are doing the LPC coefficient, and then we are remove LPC information, and then we are try to estimate beta and tau. So it will be step by step. So this one is iterative sequential approach. So we have a one shot. So and later on we are repeat again. So pitch information are recalculated based on newly formed intermediate residual. So iteration process will be continued to a certain threshold. You are or a fixed number iteration. What's the iterative? Because we try to mean, because S of n, they have a two turn to do the prediction of S of n. So it's a step by step. We assume this one becomes 0. So we try to minimize S of n close to this linear combination. So we find out the alpha. And then later on we try to this one, remove this one, become the residual. We find the tau and beta. So once we get the tau and beta, so original signal can remove this one, and then we are based on that doing again, try to find the alpha again, and then we get the alpha. So we try to find tau and beta. So it's repeat one-shot optimization many times and make a total error become minimized. Because it's not easy to do optimization based on alpha j, tau, and beta j at the same time. It's not easy. So we have a three. If we are consider this equation, so this one we assume close to 0. So according to this equation, so you can see you have an undetermined unknown parameter alpha, and unknown this one could be alpha, this one will be tau. So you have an unknown alpha, unknown tau, and unknown beta parameter. So you have a three type unknown parameter. So the best solution will be determine 3 type unknown parameter at the same time, but it's not easy. So we be each time sub 1 parameter, and each time fix tau and sub beta, and try to using different tau and get beta. So it's more like an iterative. So after one shot, and then we have this data, and then we are subtraction again using this one, subtraction this one, and then we try to optimize this one. So we call iterative. Iterative is would be include many one shot optimization to do the work. So for practical reason, so most of the case for practical reason, so one-shot method is usually preferred. So they just one iteration. We find your short-term prediction coefficient and also find out your long-term prediction coefficient. So you can see if we are LPC coefficient remove it, so we are remove original signal cross this one, subtraction this one, so become alpha n. So right now we become alpha n, try to subtraction your long-term prediction. So do the same work, we try to take square and try to minimize the error. So we try to replace it, the expectation with a finite summation. So you can see we can do the same work. This one is similar like a linear prediction. So you can get your beta according for given tau. So correlation. So V is more related like a residual signal, like based on the tau, your moving tau, to calculate their close correlation. So they try to find out close correlation. So right now you have two unknown parameter, two type unknown parameter. So you can see using the Cholesky decomposition to do the work. So according to this metric, so you can see they have a symmetric in the corresponding position. However, diagonal is not the same. So this one is a little bit like a covariance metric. So here they call the Cholesky. They're using Cholesky decomposition again. So another one, if we are trying to using try to find the pitch. So in order to determine the tau, so could be they can use in different way to do it. So you can use in the like autocorrelation or average magnitude difference or captron or maximum likelihood. Try to find the tau first. Once you have a tau, maybe you can sub the beta, or you can do the full search. Because why we can do the full search? So another way we can do the full search as well, because this tau is related to your pitch. So we know our human being pitch is around your 16 sample to around 116 sample. So human being pitch is so around this area. So we can use it like a tau at a tau equals 60. So we can sub the E of n, R of n minus ij equal to minus I beta j. So R m minus 16 minus j. So you can sub this best beta. And also tau equals 17. You can do the same work, and you can tau equal 116. So you can get E of n, R of n. Try to get the best beta. So how many you have right now. So right now you have, so you have this one minus this one. So be supposed to be they have a boundary. So total equation what you have, so will be 145. So you have a 145 equation. So according there, you find the best. Find the best. So first one, you find the best beta. So find the best beta at each tau. So you find the best beta at each tau value, and then you can see which case. So you try to find which case has the minima. So minima error. So try to find which case have a minima error. That one become the winner. So that one is more like a full search, because the tau we have a naming range. So we cannot. It's not easy for us using the deterministic equation to find the tau. So maybe we can base on different tau together. Different tau we can get your best beta, and also calculate the total error value. So we are compare each error value, which one will be minimum error. So we are the winner. So that one is very straightforward. So the question is to become reduce your problem, your equation problem become the try to sub metric equation. Okay. So you can see, so the size of our window is a block taken required longer than the analysis frame. So we hope that our tau can be vary between the minima and the maximum. Sometimes we are look over. Sometimes we look over your boundary. So you can see here. So we are look forward. Try to find the picture. Sometimes we are look forward your boundary conditions. Look forward like a neighboring friend, speech friend. Try to get the good precisely pitch. So right now they're using very simple one example. So for example, we are not consider. So last time, so previous example, they are consider. So last time we are consider. They are look forward maybe your tau, and then neighboring. We have neighboring pixel, neighboring sample, signal sample to do the prediction. So this one, if we are only consider, it's not consider multiple. We are not consider multiple sample to do the prediction. Just consider one sample. Just consider one sample to do the prediction. So we call this one is a one-tap pitch filter. So more like this definition a little similar like what we call the FIR. So if your finite impulse response have a phi coefficient, we call the phi tap FIR. So similar the same word. So here what we say, because they try to calculate the equation here. Okay. So you can see they try to P1, if P1 equal like this one, so they can get a beta and also your error function like this one. So I go back to our PowerPoint. So maybe I have some equation derivation ready up there. I double check. Maybe not. Okay. Covariance, pitch. Okay, so not yet. Okay, so here because they are one tap, so we can it's very easy to do the prediction here. So because one tap, it looks like we have a signal. Here n is speech friend, the speech sample, number of a speech sample at a speech friend. So this one is our n. So you can see how to calculate the pitch. Calculate the pitch because we have a residual signal. We call this one is of n, and then we are consider the speech friend, maybe speech friend like this one. So this one is the total your n here, and then right now we have this equation. So we are look like your r of n. So you can see your r of n. We have an arrow function here, r of n summation, because only one tap is not considered. This how to call this one? This one we call the 2i plus 1, 2i plus 1 tap like a pitch filter. So right now only one tap. So one tap is just beta, just one coefficient to do the prediction. So they have a r of m minus tau. So we try to find the moving position, move tau. So it looks like we move tau. So residual signal is a move tau position, and using this corresponding point to multiply by beta to do the prediction this point. So you can see our equation right here. However, we try to, it's not just only one simple. So we have to minimize one frame. Make sure your one frame has the same data. So you'll be more like one frame. Each point, whole one speech frame should be get the same, minimize the result. So what's your n? N will be so right now you are using the m. So m. So m from 0 to m minus 1. So it look into one frame. So we try to minimize your error. So minimize your error. So if we are consider square, so this one becomes the square. So each sample using the move the tau. So it's not just only one point, and hold the point will be move the tau. Hold the point will be move the tau, and do the prediction. So you can see our arrow function like this one. So we can easy to do the derivation for this one, this equation. So we try to because we assume tau for some specific. So right now tau is a specific value. We are assuming that one will be some specific value. So only a beta is unknown here. We try to get beta unknown here. So we try to take derivative according your beta. According your beta become the 0. So this cost function will be the minimum because it's a beta square. So this one is a second order polynomial function. so their beta become positive. Beta square is positive, so that one we have a minima value. So if our first derivative becomes 0, so the condition will become 2. So you'll be become by 2 summation n minus 1, n becomes 0. So that one is r of m minus beta, and r of m minus tau. So second order become, and look into inside there, the inside become, this one no beta, this one we have a beta, so will be r m minus tau, so they have a minus. So we hope to become 0. So you can see this one multiply inside there. So you can see here, the summation n minus 1, n equal to 0, rn multiply rm minus tau. So this one multiply inside there. So minus will become minus and plus. So still minus beta. So rm minus tau becomes square. So this one we hope to become 0. So summation put inside there, put inside here. So you can see your beta, the best beta becomes summation n minus 1, n equal to 0, rn. So this one is more like your correlation divided by your energy. Divided by your energy. So sometimes they are moved a little bit by your pitch step, more like a normalized correlation value. So if your beta become this value, so you can have the maxima. So you can see here, what's our tau? Tau we have a, suppose we will have a tau minima and tau maxima. So here minima is 16.160 sample. So we can use in different 16 substituted. So substituted inside this equation, so you can find the best beta. So what's the arrow function here? Your arrow function. So what's the arrow function? So your arrow function in here, so n minus 1, n equal to 0. So you can see it will be r square m minus 2 beta rm minus rm minus tau plus beta square r square m minus tau. So right now we have a best beta. So your beta will be substitute here and substitute here. So you can, after derivation, so after you simplify, try to simplify them. So you can get an equation like a summation n minus 1, n equal to 0. So r square m minus summation n minus 1, n equal to 0, r of m minus tau square. Because you can see this one multiplied this one become the square, and also become beta have a denominator. So you can see also you will have m summation n equal to 1, n equal to 0 from r square m minus tau. So that one just give you idea. This one is what's the beta? Beta, the best value is like this one. And then we have a best beta. We have a best beta. So we substitute it into this equation. So we can get their error, total error in this speech frame like this equation. So this one is residual signal energy. So this one is fixed. And this one is depend on your tau. So different tau, so our tau will be counted from the minima to maxima. Different tau, so this one fixed, we try to minimize our error function. So look like this fixed. So this is minus. So we try to make sure this value become the bigger. So our fixed value subtracted by bigger value, so your error function becomes smaller. So right now you have to substitute your tau to get a normalized correlation maxima. That one will be the winner. So that one will be straightforward, will be easy. It's not like this one. So this one you get a 5 coefficient. You have to be, because you have a total 148. So each tau you have 16. Substitute it inside there, you get beta and calculate the error function, error value, what's the total error value, and then tau equals 17. So you get a best beta and get the total error. And from the error, you try to find which one is the minimal loss, minimal error. Based on minimal error could be the winner. So however, here we get the best beta. We get the best beta. We get the best beta and substitute original signal. Because they are one tap, so we do not have a inverse metric calculation. So we just using the beta, substitute your original cost function, error function, and then find out, well, your error depend on your energy subtracted by your normalized because you divide by energy, move waveform energy, and then correlation, autocorrelation. So they have an autocorrelation divided by your energy, so it's normalized autocorrelation. So normalized autocorrelation. So if we are trying to find this one, maxima will be the winner. So our tau will be become from the minima, so tau minima to tau maxima. So substitute this one, normalized autocorrelation, find the maxima value. That one will be the winner. So that tau, it will be the tau will be winner, and then based on that tau we can get our beta. Based on that tau we can get the beta. So that one will be straightforward to get your solution. So you can see here, original signal, we are trying to get a remove LPC. We remove LPC, so we get a LPC residual signal. So, and then we are get the pitch signal, remove pitch signal, so become the pitch residual. So right now we get an optimal tau, and then that one could be called a lag. So we get the best tau and sometimes the best gain, beta prediction gain. Because the pitch residue sometimes will be considered, do we have a second excitation? Maybe they do not have a sharp pulse, like, because you can see original signal remove LPC signal, so you can see still have a sharp peak point here. Once we remove LPC signal, no, pitch signal, sorry, remove pitch signal, become pitch residue. So there are clearly unclear the peak point. So there's no longer possesses the sharp pulse-like characteristic of the residue. So it looks like a much white noise. So sometimes we are maybe it's not further to the modeling. So right now we get a tau and beta. So if we are 3-tap will be considered multiple move a tau on that point neighboring like a 3 sample to do the linear combination. So you can see multiple tap sometimes get a better performance because they have more combination than the single tap. So you can see most of them are standard, or they have a multiple tap to do the work. However, they're using a single tap do the prediction first, try to find approximate location and approximate tau, and then based on that kind of approximate tau, the neighboring point look into more multiple tap and do second time again. So you can see here pitch lag variation with time. So you can see a lot of variation. Sometimes this area could be unvoiced. So the pitch is sometimes a continuous variation, very smooth. That area it look like they are voice frame. So if you are unvoiced, sometimes no consistent information up there. So you can see voice, unvoiced, and transition. So you can during the voice, so beta will be close to unity. So your beta is like your pitch gain. So sometimes transition region. So what's the transition region? From the voice to unvoiced, also from the unvoiced to voice. So their beta will be maybe have big change over there. So so you can see, so they have a some transition here. One is a pitch lag. Pitch lag is like your pitch. So if you are consistent variation, this one is the voice region. So this one should be pitch gain. Pitch gain in the transient region or unvoiced region. So that one pitch gain will be have a larger variation. So your voice region, the pitch gain a little bit consistent over there. So because your energy is not big change, sometimes in one speech frame they have keep same energy there. So I repeat again using the Mandarin for this part. Okay. 这一节呢，我们主要讲的是 pitch。那 pitch 的概念呢，实际上就是我们刚才前面一章是讲的是 short-term prediction，pitch 呢比较像是 long-term prediction。那 pitch 的道理呢，实际上就是说，我的 LPG 的剩余信号好像还剩下有一些比较有周期性的 peak 出现。那我是不是可以把这个 peak 也 model 起来？那我们就所谓的pitch 的计算，pitch 的计算。那在做 pitch 的计算的时候，也就是说我原始讯号也就是说我的发生讯号本来是要用前面的讯号做线性组合，然后呢我的 pitch 呢是移了一个 t 的位置 tau 的位置。在它的附近用2i 加1的 tag， 就看你用周围多少点这个是往前看，这个是移到 tau 的位置为中心，往左右看，中心点也看往左右看，然后做线性组合预估。那 one sharp 呢是说我先找到我的 LPC 系数 alpha， 那把原始讯号减掉，这个就变成 R。剩余讯号 R， 那借由剩余讯号，我再来找 tau 跟 beta， 这个叫 one shot。那迭代式呢是说我包含很多的 one shot， 也就是说 alpha 找完，我再来找 tau 跟 beta。tau 跟 beta 固定了，我就把 s of n 减掉这个讯号，减掉这个讯号，我再来找 r。所以说呢，就是这样迭代式去优化我的 r、tau 跟 beta。一般来说，这是你的 cost function， 你有3种形式的变数。那最好的情况是3种情况的变数一起考虑来做最佳的参数的找寻。但是这3种特性都不一样，不好求解，数学很复杂。那就代表说一次一个系数来优化，但是优化的时候就会把这个 condition 省略掉了。那虽然你迭代式是慢慢这个因素有被考虑进去，这个因素化，实际上它的情境有点像前面在解 LPC 的解 LPC 解是一模一样解 LPC 解一模一样。那你如果去算求解的话，我对贝塔做偏微分，它实际上对假设 tau 是某一个固定值，对贝塔偏微分，你就会得到类似是这个矩阵。那这个矩阵当然是跟你的 correlation 有关，你看 alpha 呢是以 tau 的位置 correlation，vij 呢是对应的 tau 附近的 i 跟 j 的一位的 correlation， 所以说呢它也是 correlation 矩阵反矩阵求解。那它的矩阵呢不是对称矩阵，也就是对角线不一样，那它属于那种 covariance 矩阵，可以用 Cholesky 的解法。好，那这个我们地方不会去讲细节矩阵求解。那其次的话，他有说到你的 tau 怎么决定，你可以用之后会讲 autocorrelation 方法ANDF captron 或怎么样去找 pitch。那这边有一个 tau 呢，实际上我们刚才在举那些 tau， 实际上我刚才有讲，实际上 tau 因为人类的 pitch 不是无穷多种组合，实际上它是有一个限制，有一个限定的范围。那这个限定范围呢，我实际上可以善用这个限定 tau 的限定范围。那我就利用假设是课本所解的16到160，那我就会有16到160这么多的 tau， 每一个 tau 呢我都可以找到最佳的贝塔。那相对最佳贝塔，我就可以针对这个音框所看到的，这实际上是一个点，但是真正的 error 是要整个音框去看整个音框都是对应到同一个 tau 一组贝塔，然后去做移位配对，去算出 error， 那让整体的整个音框的 error 最小，那个 winner 就是我的贝塔跟 tau。那虽然这是一点，但真正的 error 应该是全部整个音框。那在固定的某一个 tau 值算出一个最佳贝塔，整个音框去算，就刚才反矩阵求解。那把那个贝塔带进去之后呢，再算整个音框依照这个参数所算出来的 error。那我这边 tau 等于16的 total error， tau 等于17的 total error， 那哪一个 error 误差最小，那就是 winner。那但是呢，这样当然是会比较复杂一点。那另外一个呢，如果你的 tau 是一个1那在它这边 tau 是1呢，实际上就有点像 FIR one tap FIR filter， 所以它这边用 one tap 的 pitch filter 来看。那如果你 tau 是1的话，我的式子就可以做某种程度的简化实际上就是我移 tau 的位置，就在那个位置乘上一个贝塔并没有看太多的讯号。那我实际上是要 minimize 整个音框，所以说我考虑的我的音框，那整个音框移了 tau 的位置，要对应那一点乘上一个 scalar gain， 希望你的 total error 变小。那因为我的变数，我假设 tau 先固定，我对我的贝塔做偏微分，那你就会得到这个样的一个条件等于0，因为它的贝塔是平方是2次4，它的平方2次4是正向，那你的贝塔就会得到这个系数。那得到这个系数之后呢，你就带进原来你的 cost function， 你可以把这个 cost function 展开。 那带进去，把这个贝塔带进去，有贝塔平方，那这个能量出来，那这两个做组合就会得到这个式子。所以说代表什么意思呢？我希望我的 total error 最小，代表说我的这个能量是不变的，因为你的剩余音框的讯号特性是固定的，所以说这个是讯号音框的能量是不变。那唯一的就是说我要 error 最小，这个值要最大。那这个值实际上就是移位的能量，移位音框的能量乘上移位对不移位之间的 autocorrelation 的关系。那因为除掉能量，我们称作 normalized autocorrelation。那我的从 tau minima 到 tau maxima， 比如说我可以从16点到160点，在 h 点723.1，它的标准好像是从18到142，它并没有那么多，为了是2的7次方，128种，好像这只有125种，它没有考虑那么多。那所以说呢，它实际上因为 tau 将来是要 encoding， tau 的移位实际上是要用它的位置的组合，就是我要 coding 的 bit。那很清楚的就是说，我实际上呢，我就不用像刚才你的 beta 有很多组去看最后的 error， 我直接就算 tau 用哪一个值，它的 normalized autocorrelation 最大，那我就知道那个 tau 就是我要的 tau。那你已经知道你要的 tau 之后，你就可以去算你的最佳贝塔。那另外一个，那这是原始讯号，那去掉了 PC， 因为你可以发觉还有一些比较周期性的 peak， 那我们就想办法移位乘上 gain 去消除它的讯号。那如果我把pitch 讯号移掉，他觉得这个有点像是 white noise 了。实际上，这个剩下的讯号是人类说话的特质了，有一点像不同人之间的说话特质。如果你只用 LPC 语义出来了，你找出 pitch， 男生女生有分出来，那个音调的变化有分出来，那人的特性也有分出一点点。那但是如果你的剩余信号再保留，部分的保留，那个人的说话，张三李四说话的一些的个人的特质就保留更多了。那所以说接下来他讲，一般来说 multiple tap 当然比 single tap 好，因为 multiple tap 你可以说multiple tap 的特例就是 single tap， 为什么？但既然你用3个来插补，我假设是加1跟减1的那个贝塔值很小或接近0，就是 single tap 了。所以说实际上当然 multiple tap 效果应该要好，因为整体 loss。那这个是说我们来看一个有声跟转换区间，一般人类在有声的时候 pitch 的变化不会那么快，它虽然可能一下讲得很快，一下讲得慢了一点点，它 pitch 有一定的连贯性的变化。当你在有声到无声，无声到有声，因为你的公式去做配对的时候，就会发觉有很大的差异。无声的时候根本它配不太出来。那如果你去看你的 pitch gain 的时候，有声的时候这个 gain 呢大概都会一致，因为人类说话能量不会差异太大，短时域不会差异太大。那但是呢，在转折或是无声的时候，因为它的 model 不见得是完全是 model 到有意义的讯号，往往变化就会大。OK， 大概这是 pitch 的一些概念。Okay, so in this chapter, we are talking about source filter model. So we are from the OPPO model. We start from the OPPO model, and also we are consider LPC and pitch. So LPC is like a short-term prediction, and pitch is more like a long-term prediction. So LPC is more like a short-term similarity, and pitch is more like a long-term similarity. So all of this similarity or redundancy we try to model by your LPC and also pitch filter formulation. So the redundancy sometimes we are removed from the analysis stage to reduce the bitrate required for transmitting the remaining residual signal. So during analysis, your speech obtained a short and long-term filter coefficient, so reasonable lengths of a sample are needed. So sometimes we be consider your speech frame how big. So most of them they are using 20 to 30 milliseconds, so they cover around 160 to 240 sample at 8 kHz sampling rate. So however, sometimes most of them they are using LPC filter will be 10 order. After 20 milliseconds will be update their LPC. So 1 second will be cover 50 frame. So this one related to linguistic, like your phonic, basic sound, like REVO. So this one is related like your basic sound here. So however, like your pitch is like a single order long term, sometimes they will be updated more frequently because pitch signal, if you are synthesized at a long speech frame using the big speech frame at the same pitch period, that kind of synthesized decoder signal look like a machine sound. So we have to make sure our synthesized speech signal look like a human being speaking, similar like a human being speaking. So the pitch should be a little bit variation. So they're using the small speech frame to do the update your pitch frame. So in the standard, they are, for example, 3.7 or 23.1, they are standard. So they try to partition your speech frame. So so become the 30 millisecond, and also this one 240 sample, and then they partition 4 subframe, 60 by 60 by 60 by 60. So they will be calculate LPC. And then calculate LPC in the between subframe. So we call this one will be subframe. So they're using the linear interpolation. So using linear interpolation your LPC. So your LPC have a little bit variation, and also they have a pitch here. So they have a pitch here. So the pitch search using this subframe do the pitch search, and then this one pitch. So you have pitch 1, pitch 2, pitch 3, pitch 2, and this one will be pitch 4. So pitch 4. So pitch 1, pitch 3 will be search, and pitch 2 will be according pitch 1 have some variation. So variation will be +1, +2, 0, and -1. So this one will be have a 100 around 125 position search. So they have so many position search around the 2 power 7 position, because later on we have to coding it. So this one will be coding this one to do the search. So they have a variation here. So this one will also do the 125 position search to find. So you can see from the standard, most of them try to keep some LPC have some linear interpolations. They based on subframe to calculate, and also pitch. So they have some variation according to subframe. So most of them like a 60 samples. So this one divided by 4, it could be 7.5 milliseconds. Have a little bit change their speech frame. So they try to, because during your synthesize, so in this speech frame, the signal have some pitch variation. The synthesize, we want to make sure our synthesize speech signal, maybe we can call it decoded signal. So crow similar, like a similar, could be similar to human human speaking. They try to like a human speaking. Human speaking waveform is not a machine speaking. So sometimes your pitch is fixed. Pitch is a fixed one value. So your synthesized speech waveform, human being to hear that kind of waveform, well, a little bit like a machine sound. So we have to avoid that kind of situation. So like a standard, most of them, they try to keep some variation in by using the subframe to do it. Okay, I use the Mandarin to conclude this chapter. 那这一章我们介绍了short-term prediction 跟 long-term prediction， 那蛮多物理意义。那数学我并没有深入，那有一些基本的数学概念我有给大家。实际上 LPG 在求解实际上就是矩阵反矩阵求解，去算它往前去看的线性组合。那 long-term prediction 实际上某种程度就是移位，去多了一个移位，那用周围的点去做线性组合。那这些线性组合最后解都是变成反矩阵求解。那唯一的 pitch 呢是变成多了一个 pitch。那还好，这个 pitch 人类的 pitch 呢并不是无穷大、无穷的动态范围，它是有一定范围哈。那我就可以 based on 这个有限的范围去做搜寻，找出一个最佳的 pitch 点，然后对应的 pitch gain， 那就可以做一些优化的 model。那一般来说，我希望要去取到这些 model 的参数，你的音框的内容要足够，否则我 model 的效果不好。那蛮重点的是那个 pitch。好 ，pitch 如果大音框，你不能只给一个 pitch， 也就是说，当我的音因为我的 pitch 有可能是从课本16点到160点，那我的音框如果是240个 sample， 只有一个 pitch， 那很麻烦。当这个人的 pitch 是40了，我240点 pitch 是40 ，240点我会有几个 pitch 会有8个 pitch， 这8个 pick 点。这8个合成的8个 pick 点，这8个 pick 点都一样的距离，那人听起来就会像机械音。好，所以一般来说，在合成的时候，或是在 model 的时候，尽量用考虑到小的音框，或者是它们音框之间的较小的音框的变异性，甚至在合成的时候都会加一点 variation。让它听起来比较像人类，因为人类的喉门开关做 trigger， 它不可能是一个固定的 pitch 因为生理机构没那么准。那实际上只是短时域来看，它好像的周期有相似性，那周期有变化，但是变化不会那么差异那么大。突然我用了很尖的话，突然我用很低沉的话，那个 pitch 是变的，但是从人类的机制上去做反应，它切很短的时域，它的 pitch 变化没那么快，所以我们可以想办法假设短时域来看，很短的音框来看，它的 pitch 是固定的，我们是这样。那如果你音框某种程度大了，那 pitch 又短，那这时候就会造成 pitch 没有变，那听起来就像机械音，会有物理意义是这样。Okay, so this one is our chapter 4. So we got a coefficient, pitch coefficient, and also we have a short-term prediction coefficient and long-term prediction coefficient. Our main purpose try to do the encoding. So right now we have to think about how to encoding them. So in chapter 5, so their first issue try to think about how to quantize LPC's coefficient. Because you have a 10 coefficient, like a P equal to 10, so you have a 10 coefficient. So we have to think about how to do the quantization. So here they're talking about that one method they call the night spectrum pair. So you have two issues you have to focus. During your quantization, you have a stability issue because you are open model. So you have to think about you have a stability issue. Make sure because you are open model. What's the pitch? I'll go back equation. What's the pitch? No, it's LPC from the beginning, what we're talking about in the beginning. Okay, so this from the beginning, this one is our open model. So we got our alpha here. So it's our short-term prediction, linear prediction coefficient. So you can see this one, what's that? It's not a pole. This one is not a pole. This one is your polynomial function coefficient. So if you are trying to see this equation, so it's h of z. So it's more like a g1 minus summation p j equal to 1 aj z minus j. So you can see this one is 1 minus, so it's a1 z minus 1 plus a2 z minus 2 and so on. So you can see this one, this equation, what we have is ap z minus p here. So what we get here, we get that this one is our LPC coefficient, you know. So because this one is an open model, so we supposed to be, if you can transfer like 1 minus pole 1, so we have a pole 1, maybe we have pole 1 minus pole 2 maybe the other way. So we hope to, you have a pole 1, maybe like a pole 1, like a pole 2, you have a pole 3, pole n. So this one is your pole. So it's not like this equation. We got is polynomial equation coefficient. It's not a pole, open model pole. So this is Z transform. So Z transform supposed to be you are trying to be stable. It should be in the unit circle. Should be inside the unit circle. So S domain is the left hand side. So you are Z domain. So you have to make sure your pole inside the unit circle there. So because we get the coefficient here, and then we are do the quantization, we have to your open model, the pole should be inside the unit circle. So they have a stability issue. So right now we have a 10 coefficient. Right now P equal to 10. So we have a 10 coefficient. So 10 coefficient, we try to reduce their bit rate. So we try to reduce their bit rate. We have to consider how to quantize, efficient quantize. And also during the quantize, you have to consider make a filter stability check. You have to consider how to do the stability check. So most of popular LPC transformation, they are considered night spectrum pair. So later on we are define what's the LSP, night spectrum pair. So some guy will be talking about define the night spectrum frequency, depend on how to define it either way. So night spectrum frequency is the same as a night spectrum pair. They are same same term using different definition, so they are same meaning. So LSF or LSP, either way is okay. So we have to consider we are model this one doing the quantization and make sure they are stable. So however, we have to do some, if we are H of Z stable, so they have the meaning phase, all group should be within the unit circle. So we have to consider this issue. So alpha I are quantized directly, so you can see the stability filter is not easy guarantee. So we have to consider, if we are consider during your quantization, you can synthesize to transfer the other domain parameter. That parameter during the quantization, we can check. During the quantization, we can do the checking the stability. We can check in the stability. So we can know what kind of value do they stable. If not, we have to check using different quantized value to represent the parameter. Once we get a quantized parameter, we can inverse transform to LPC coefficient. So right now, supposed to be we are trying to quantize LPC directly. So sometimes we are after you get a quantized LPC coefficient, you didn't know original transfer function is stable or not. So right now we are in the other way. So LPC coefficient will be transferred to the other parameter, and then based on that kind of parameter, we are doing the quantization. And then that one easy for us during the quantization, we can check whether do they stable or not. So once we get a quantized parameter, they also be stable. So during decoder, they get a quantized parameter, they can be inverse transform to become LPC coefficient. So you have LPC coefficient, you can do the short-term prediction to recover back the signal. So here they're talking about a PACO. LPC to PACO signal. So LPC to PACO signal, so maybe you they give you the equation here, and later on I will teach you what's the PACO physical meaning. Right now they just show you the equation, so you just take it, and later on I will be teaching you what's the physical meaning of the PACO in the maybe 2 sections later in this chapter in different section. So LPC, they based on this kind of transfer from original is alpha I, so they are transferred to become the PACO coefficient. So PACO coefficient is K. So you can see K will be smaller than 1. So suppose if we are trying to stable, PACO coefficient should be smaller, the absolute value should be smaller than 1, 0. So we can, during the quantization, quantize the PACO coefficient, so we can know they are stable or not. So another one, so we are take the PACO, so we have a PACO coefficient, so we are also try to transfer the PACO coefficient to another one. We try to using log area ratio, so they are do the other modified version. So first issue, we have to transfer to the PACO coefficient. So all the coefficient they are distributed between the -1 to 1, so they are 1 by 1. So we have an order, P order is 10, so they corresponding have a 10 PACO coefficient. So they have a 10 PACO coefficient. So another one based on, once you got a PACO coefficient, so they try to normalize their distribution using the sign. So you can see they're also using the sign to do the transfer. So this one sign, you can see their distribution. So this one using the log. and another one using the sign to change their distribution. Sometimes they try to, because different transfer, so sometimes will be using supposed to be original distribution. Some part become linear, some part become non-linear, become log scale, some part become some sign. So they try to highlight some important part, because they try to highlight important part close to 0, so they could be using some transfer signal first and then do the quantization. So the main idea, first issue, because we are considered during quantization, we know the signal, we try to know our transfer function can be open model, known short-term prediction is stable. So we are transfer our LPC to the PACO. So we are transferred to the PACO coefficient. So based on PACO coefficient, we can quantize that, and also we can do the like a log scale transfer, or could be do the sign transfer. So this one just change their distribution and make a good use of your quantizer. So the physical meaning is like this one. And then once we are quantize this data and dequantize and transfer back so to LPC coefficient, so we can synthesize back original signal. So in this chapter, the first part, they try to talking about during the quantization, you can know your filter is stable or not. So maybe original coefficient is not related to your pole. So we have to transfer your coefficient to the PACO and make sure the PACO coefficient is related to your pole. So that one will be make you during the quantization, you can double check the filter, original filter, do they stable or not. So that one is the main idea here. Okay, I'm using the Mandarin. 这一章开始呢，也就是说我前面已经找到了 pitch， 找到了 LPC 系数。那这一章主要的重点就是说我针对 LPC 系数我要怎么量化。我有10个系数，如果我不量化，它的资料量蛮大的。那我要量化的时候又很麻烦，因为我原先的 Open Model LPC 呢，它是这个多项式的系数，不是它的 pole， 不是它的 pole。那不是它的 pole 就会麻烦。好，实际上我要写正确的话，会是1减 z 的负1， 1减 z 的负1。哈，实际上如果依照这个公式是1减 z 的负1， 1减 z 的负1。好，那实际上如果写正确了，哈，对不起，实际上是1减P1 的 pole z 的负1， 1减P2 z 的负1。哈，应该是这样，1减 P。第 P 个 z 的负1，第 P 个 pole。那所以说我要知道，因为这个 pole 呢必须在 unit circle 里面，哈 ，unit circle 里面或者在 unit circle 内，哈上都可以，那它才会 stable。那所以说呢，也就是量化过程，我能知道它能不能收敛。那我能不能把 LPC 系数做一个转换成另外一个系数？但是它必须能 perfect， 能用 perfect reconstruction 啊，要像。不能转换过去转不回来，那就没有用。转换过去，我直接就针对这个 PACO 系数做量化。那这时候 PACO 系数做量化，我的量化过程就可以或量化系数有没有在小于等于1？如果小于等于1，代表我的系统会稳定。那 PACO 系数呢，可能它的动态范围我有兴趣的，因为它需要绝对值小于等于1，有可能我希望的值在0的附近。要比较重要，那就是说负 0.5 到 0.5 比较重要， 0.5 到1，负 0.5 到负1，可能值的重要性没那么大。那我可能会把这个分布曲线做一个转换，用 log scale 的转换或 sin。那 log scale 当然它用的是有一个加一个减的除，好，得到了式子。转换完我再做量化，好，或许说我的physical meaning 它的物理意义。比较能保留，也就是说我希望让我的量化失真， 比较 sensitive 讯号比较 sensitive 的地方也就讯号比较 sensitive 的地方，让它失真的比较小。讯号针对那个讯号的值比较不 sensitive 的地方，失真比较大，没有关系。但是我如果是 uniform quantizer 的话，我希望做一个转换，那让比较 sensitive 的地方，它的线性度、它的动态范围是拉大；比较不 sensitive 的地方，它原来的分布动态范围是缩小。那这时候我用 uniform quantizer 效果就可以让它的特性放大。那这个大概会是这样。Okay, so in this chapter, in the beginning, so we are consider how to quantize our LPC coefficient. So LPC coefficient quantization, they have one issue. First issue is stability. So here they're talking about we are not direct quantizing, so we are do the transfer to the other coefficient we call the PACO. So PACO, the coefficient, the absolute value should be smaller than 1, so that one your filter, OPPO model filter is stable. So later on, later section, I'll be talking about what's the physical meaning regarding the PACO. So this is the end of this section, this lecture. So we'll be talk to you next week. Okay, that's it.